Hello. So imagine this. You're in school and your math teacher is talking about some quadratic equations. 5 minutes later, the board looks like an ancient scripture. Yikes. And now you're gonna learn whatever the hell this is. Ha, here we go. So let's start from scratch. What is a quadratic? Quadratic comes from a Latin word quadratus, which means square. And hence, a quadratic equation is an equation with the highest power of 2. That is ax squared plus bx plus c, where a is not equal to 0. Because if a is equal to 0, this term would disappear and it would be a boring straight line just like your life. Now let's see what teasing a, b, and c can do to our equation. A determines how steep the quadratic curve is, b influences the turning point of the curve, c determines the y-intercept of the curve, which is where the graph intersects the y-axis. But that's too complicated for my brain to understand. Let's slow down a bit. Firstly, this is what a quadratic curve looks like, a very thick banana. In maths, this shape is called a parabola. The value of a determines how fat this banana will be, whether it will be upside down or downside up. If a is positive, the graph will be a smiley curve, or in other words, a minimum curve, as it has a minimum point over here. If a is negative, the graph will turn into a frown curve or maximum curve, having a maximum point over here. The value of b influences the turning point of the curve, but we'll get to that later on. C determines the y-intercept of the curve, which is where the graph cuts the y-axis. Okay, that's cool and all, but how do we find the values of x from this monstrosity? I'm glad you asked. Some random guys with too much free time with the ancient earth found this formula, and it looks kinda wonky, but you just have to put the values of a, b, and c in these places to get the values of x. Another way is by factorization, which uses this concept. If something times anything equals 0, that something can be 0 or that anything can be 0. Now what does this mean? This is done by breaking the middle term and writing it so that we can factor out specific terms. Like when we want to solve this equation, we smash 5x into 2x plus 3x because 2 and 3 are factors of 6. So we can take out x from here and 3 from there. We are left with x plus 2 times x plus 3. Then we equate each of these factors to 0 and get x equals minus 2 and x equals minus 3. Well, what about when the value of a is not 1? Then we multiply a with c and get minus 8. Then we scroll through the factors of minus 8, which are plus or minus 1, 2, 4, and 8. If we take plus 4 and minus 2, we can write the equation as 2x squared plus 4x minus 3x minus 4 equals 0. Then we factor out 2x from here and 2 from there and get 2x minus 2 times x plus 2. Nice! Hey, did we just get two values of x from one single equation? That's pretty whack, and this is where things get kinda interesting. There's a weird rule that somehow always works. Whatever the highest power is, that's how many solutions the equation has. Highest power of 2, 2 solutions. Highest power of 4, 4 solutions. These solutions can be real, equal, or imaginary, just like your love life. Quadratic equations have a fancy something called a discriminant. This thing is used to determine whether the quadratic equation will have real or imaginary roots. I present to you the discriminant b squared minus 4ac. Yeah, this is just this term from the quadratic formula, and depending on its value, we can determine the nature of roots. Let's replace b squared minus 4ac with a big D. And if b squared minus 4ac is equal to 0, then the quadratic equation will have two real and equal roots, meaning they technically have one solution, as plus 0 and minus 0 mean the exact same thing, so it just disappears, leaving us with only one solution. But it still has two solutions, just with the same value. If b squared minus 4ac is greater than 0, that means the quadratic has two real and different roots. The d is positive and we first add root d with this, then subtract root d from this and get two different solutions. If b squared minus 4ac is less than 0, then that means the quadratic has two imaginary roots. Because your d becomes negative and this part of the formula becomes imaginary, so the entire thing becomes imaginary. So we get imaginary values of x. Terrific! Alright, now let's get bendy. Remember about the parabola shape we talked about? Yeah, seems like this is kinda important. Well, we know about the y-intercept, that is the c value. What about the x-intercept? These are just the solutions of the equation. Basically, where x is equal to minus 2 and minus 3, the y is equal to 0. We found these solutions before by using factorization. Through one intercept, the graph goes down, and through the other, the graph goes up again. Now what about when the equation has one solution? The graph literally kisses the x-axis and leaves it forever as it has two repeated roots. It goes down and comes up from the same point, and yes, it still has two real roots just with the same value. What about imaginary solutions that we talked about earlier? Well, there are no solutions, so in reality the graph never touches the x-axis. It just kinda chills with a long distance relationship. Okay, ever wondered how to find the turning point of the parabola? Yeah, you haven't, but this is beautiful. Take a look at this. X squared plus 0x plus 0, which is just x squared, an upside down banana, with a turning point at 0, 0. Okay, now let's shift it up and down, shall we? At the C term, x squared plus 0x plus 2. Now the turning point is 0, 2. Damn. Can we shift it left and right? Of course we can. We can create an x shift by doing stuff inside the square thing over here. If we add a number to it, the graph shifts leftwards by that number. If we subtract the number from it, then the graph shifts rightwards. So x minus 2 whole square plus 2 has a turning point 2, 2. X plus 3 whole square plus 2 has a turning point minus 3, 2. Now you might ask, how the hell is this a quadratic equation? Well, if we expand this using children's formula, we eventually end up with a quadratic equation. Hey, fun fact, the x-coordinate of the turning point is just minus b over 2a. And if we get the x-coordinate of the turning point, we can also get the y-coordinate of the turning point by substituting the value here and getting the y value of the turning point. Now there is another method of finding the turning point of any quadratic equation. I introduce to you completing squares. Sounds like something kids would play, but it's really useful in these cases. Take this equation. First, we divide b by 2, thus 4 over 2 gives us 2, and then we simply write x over here, the sign over here, and 2 over there, and square the entire thing. Then we subtract this squared from the entire thing, and we add back the c value, that is 3, and then we simplify. Thus we get x plus 2 whole square minus 1, and we just learned how to find the turning point from here, that is minus 2, minus 1. Okay, cool, but what about when we have a naughty value of a? First, we separate out 6 from the entire expression. This is our new expression. Then we continue with our previous method. We divide 1 over 6 with 2. Then we write x and minus comes over here, then 1 over 12 there, and then we square it. Then we subtract 1 over 12 whole squared from this, and then we add back the new c value, which is minus 1 over 3. Then we simplify inside these brackets and get this. Then we simplify inside these brackets and get this. And then we multiply the 6 with everything. The turning point is 1 over 12, minus 41 over 24. The 6 over here doesn't matter, as this controls how fat your curve is going to be and not the turning point. Oh, that was a lot of work. Oh, by the way, this is exactly how the quadratic formula came to life. We said this equal to 0, divide everything by a, then take this on the other side, then write x here, plus sign here, divide b over a by 2, and write b over 2a here, then subtract b squared over 4a squared from here, and take this on the other side and simplify. Then we take the square root and we simplify further, and get this formula. Nice. Another thing is that the x value of the turning point is always the line of symmetry for a quadratic curve. A parabola has only one line of symmetry, and that is this line. Now here is where things get interesting. Believe it or not, your car's headlights use quadratics. Let me show you. Imagine you have a car headlight and the base of the headlight is a parabolic shape. Then we have a small bulb over here, and our main aim is to reflect all of the light coming from the bulb and point it directly upwards. Now where should the bulb be? Here? Nah. Here? Yep. And in math, this point has a specific name. The focal point of a parabola. Before getting into how to find the focal point, let's take a look at another important thing called the directrix of a parabola. This is a line that is constructed when the reflected ray is sent downwards by the exact same distance between the focal point and the incident point. This is called the directrix. Okay, now how do we find the focal point? Well, the x-coordinate of the focal point is the x-coordinate of the turning point. Now what about the y-coordinate? It is k plus 1 over 4a. K comes from here and a comes from here. The derivation of the formula is like a complete mess, so please spare me for now. The equation for the directrix is y equal to k minus 1 over 4a. Because k is the y-coordinate of the turning point, if we add 1 over 4a to this, we get the y-coordinate of the focal point. If we subtract 1 over 4a from this, we get the y value of the directrix line. Okay, well there goes one application of the quadratic equation. What about another? Imagine you're a farmer. You got a total of 50 meters of fences, and now you want to make the biggest and fattest rectangular garden possible with these 50 meters of fences. So step 1 is to assign variables. We're going to take length as x and width as y. The total perimeter is x plus y or 2x plus 2y equals 50 meters of fence. By simplification, x plus y equals 25. Let this be our equation uno. Now we want the garden with the largest area, which is length times width, or x times y. we can replace y for 25 minus x from our equation uno, then we multiply, we have 25x minus x squared. Wow, a surprising quadratic equation. Now let's examine this. This is a maximum curve, meaning this has a maximum point, and we're trying to find the maximum area, so let's do it. We find it using minus b over 2a. A is minus 1, b is 25, so minus 25 over minus 2 is 12.5, so we get our turning point at x equals 12.5, meaning this gives us the maximum area. The x was our length, so length is 12.5, and our width is 25 minus 12.5 equals 12.5 as well from our equation uno. And thus we get our biggest rectangular garden. In fact, it's a square. Weird surprise. Anyways, I hope you at least learned something from this video, and I hope you enjoyed it. Thanks for watching. Make sure to click the like button and slap the subscribe button. I'll catch you next time. Bye bye.